Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. Knowledge is power, now more than ever.
All right. Hello, my name is Charlie Camarda. I was an astronaut on Space Shuttle Discovery on the return to flight mission following the Columbia accident. I will be your host today for the Leading Edge Discovery podcast series, where we are going to talk with experts from around the world on the importance of science, technology, engineering, and especially research. Our first season of episodes will focus on NASA and the world of aerospace. In particular, we're going to zoom in on the Columbia accident, what caused the problem, and how did we get astronauts back up and flying safe. This is something that this is a topic which is near and dear to my heart since I flew on that return to flight mission. And I really want this to serve as a tribute to the real heroes that were working to actually do the very difficult analysis and testing, which led to us to be able to fly back in space safely. And my guest today is Dr. Edwin Fasanella, a good friend and colleague from NASA Langley Research Center. And Ed is a subject matter expert in the field of impact dynamics. Ed, welcome to the show today, and it's good to have you here. And what I love to do in the beginning of this series is have you tell your story. What got Ed Fasanella interested in science and eventually lead to the unbelievable role you played in return to flight of Space Shuttle?
Well, thank you, Charlie. It's a pleasure to participate in your podcast. I guess I was one of those nerds, that just was crazy about science from a very early age. I got into ham radio. I built my own equipment. I loved electronics. I joined a science book club when I was probably preteen and read everything I could. I subscribed to Scientific American, and we just had a good time, building things and so forth. Well, then I took off, and after to college, I went to NC State University, and I was going to major in electrical engineering, but I couldn't decide exactly what field, and I put down engineering physics. Well, it so happened that the physics curriculum had broken off from engineering, so I ended up in physics. But that was still a good match for me because I really like all of the sciences. So after I graduated from State, I went to Duke University on a fellowship, and I got my PhD there, more or less on radiation damage to amino acids and so forth, which was quite a bit different than what I ended up doing years later. After that, I went after graduating with my PhD, I taught physics at Stetson University for 4 years. And then unfortunately around the 70s, things went with the shuttle program, with the space program coming to sort of a ending point. I actually saw the last Apollo 5 go up at night. It was a beautiful thing. My kids enjoyed it too. But I ended up, there was no one going into physics or engineering. And so I ended up taking a job at Martin Marietta in Orlando, Florida. And then things got bad. The program on missiles, the SALT treaty came along, and I ended up getting laid off there. Well, that's when I ended up coming up to Virginia and hired in at NASA. Not actually at NASA at that time. It was the NASA support position. And I worked those for a number of years with various contractors, including Martin Marietta. I got into a branch called the Landing and Impact Dynamics branch. They actually put us in the branch, and we worked with the people in the branch. And I was really good at electronics, so I studied all the instrumentation on impact, became an expert in accelerometers and all other types of instruments that are used to measure impacts. And we crash tested there at the Landing and Impact Dynamics facility, many aircraft over the years, probably 50 or more. And we learned a lot on how to collect the right data and how the dummies reacted on human tolerances, on structures. And
Hey, Ed, can I stop you there for a minute, Ed, because I'm learning. I thought I knew you, Ed. I've known you ever since you've been working at Langley, because I started working in 1974 also. I did not know that you started as a physicist. One of the other fellows, a good friend of mine, Steve Scotty, that you know, also started as a physicist. So you come to Langley, and you were there at a very great time. And I'm trying to figure out, how did you end up getting into structural mechanics and the study of crash behavior and due to impact? And who were some of your mentors? How did this come about?
Well, it's a lot of serendipity in this stuff, Charlie. I was actually I was actually looking for a job, and so I applied, and there were several positions that came open. One of them was impact dynamics with Bob Thompson, who was the branch head then. And I love physics, and I love Newtonian mechanics and that type of thing. I said, and there was another position that was open, but I like the impact dynamics one better. So I go in, and I'm working with Huey Carden and Bob Thompson, Emilio Alfaro, Bob Hyduke, who worked at Washington headquarters for a while, and got really involved with structural mechanics, because I always have, like, in addition to electronics, I always loved mechanics, and especially impact dynamics, structural dynamics.
This is amazing, because the facility that Ed is describing, when I first started working there, looked like this gigantic erectisect gantry of a structure, where the first 7 astronauts were training at NASA in the early Apollo days. And they actually practiced landing on the moon and simulating 1/6 gravity landing on the lunar surface at your facility.
That's exactly correct, Charlie. And I came to work there right after they closed that down, of course. And they had lots of pictures of the moon there, and they had the pictures of the simulated surface. And then there was the conspiracy theories. Well, it was all filmed there. It wasn't really on the moon anyway. But yes, that was the history of the gantry. And the gantry was a very interesting and unique facility for many years. And I worked there, and I was afraid it was going to be torn down before I left, but it's still there. But I imagine it may not last too many more years. It is getting to be an old structure.
And as a matter of fact, you used to swing these general aviation airplanes, helicopter structures, to study impact dynamics. And one of the latest things you did there was actually the impact test of the Orion capsule in land and also in water out there.
That's exactly right. When the Orion program started, a large water basin was created so that we could swing in the capsules into the basin. And in addition to these tests, I was like an experimentalist and analyst. I knew both sides. A lot of people know one or the other, but I was lucky enough to and interested enough in both that I could work both sides. So I started working LS Dyna and a lot of these impact finite element programs that really got very good, because they had been started out at Lawrence Livermore mainly for the nuclear industry and then car crashes. So these finite element programs became very good, so we could actually predict what's going to happen when you impact into water, onto land, or just to most any surface. We called it multi-surface impact analysis. So we could actually predict pretty much what was going to happen before the crash occurred, with good results in most cases.
And so did you have to get additional training? For instance, you mentioned finite element analysis, which is a numerical technique. Now you're using this at ballistic speeds and trying to understand the dynamics, the crash dynamics of what happens. Did you have to go for advanced training and advanced courses in finite elements?
Well, Charlie, you may remember the course we took together back many years ago under Ahmed Noor. That was one of the theoretical courses I took. Obviously, I went to LS Dyna training and many training courses on the theory behind the methods that were used, and a lot of the tests and a lot of sample cases and learning LS-DYNA in a complicated dynamic finite element code that goes into plasticity and failure and that type of thing is very difficult because failure, if you delete parts out of your model, it makes the model, if you're not careful, it makes the model unsteady and it can go crazy. But yes, I have a lot of training, and of course I enjoyed that. We'd go to various locations out at Lawrence Livermore, or we would have instructors come in and train our whole group. So it was yes, quite a bit of training was required specifically on that code. Now I knew a lot of the basic physics and stuff like that, but there's a lot of higher mathematics, and the finite element method is complicated.
I thought, we had taken several classes with Dr. Amin Noor, right, at George Washington, who was a leader in finite element analysis, which is a numerical technique. I remember going to a short course at MIT, and I can't remember the name of the dynamics professor that was showing impact results. And it looked like they were tests from folks at Sandia, where they were looking at developing the bunker busters to get Saddam Hussein. And they were actually predicting how these shells were going to deform as they were going through the Earth's surface, which was amazing to me.
Yes, MIT, I'm trying to think of that. I'm trying to think of the professor. I know who you're talking about. Unfortunately, sometimes I have a problem pulling names in, but yes, it's amazing what these impact codes can do, and they've just gotten better and better. And now they design almost everything. It's even Coke bottles are designed for impact, and so they won't burst open. Car crashes, nuclear containment, you name it. It's bunker busters. It's just amazing what can be done. And of course, the work on the shuttle leading edge was another leading edge, another leading pioneering effort, I guess you might say, trying to model foam impacts onto a complicated leading edge material. So we had to learn a lot to do that, and we did learn a lot. And you have to do a lot of experiments too, in addition to just, you have to know the material properties of everything, metals or foams or ceramics or composites, or you have to know all the material properties and how it behaves dynamically too. And the mass comes in quite important inertial effects.
Ed, a lot of our listeners don't understand how long it takes to actually mature and develop and mentor a person to actually be an expert in these fields. And in your case, it was you were practicing approximately 30 years in this field, doing lots of tests, learning your craft, and you worked on some amazing programs. And one of those programs, which I just realized as I was researching you that I did not know you were part of, was the controlled impact demonstration. And everyone watched this on TV. Could you explain that a little bit to us?
Well, yes, Charlie. I spent like 5 years working that program from the day one till the day it ended, till writing a bunch of reports on it. It was a very interesting. It was probably the most interesting program I had worked on before the shuttle impacts.
Could you describe what it was for the audience?
Okay, well, the FAA came up with the program, and NASA joined because they needed some expertise. And the program was, you take a 707 aircraft and you load it up with dummies. The main test for the FAA was to prove that a so-called anti-misting kerosene would not blow up and would not mist and then ignite with a fireball. And the FAA had done a lot of tests up in New Jersey on this, and we would go to New Jersey quite a bit and talk with their research people and their engineers and so forth. And it was the whole test was a little scary from the very beginning. The NASA side was very concerned about how it was going to come off. The plane was guided by Fitzhugh Fulton, Bob Fulton's brother, who was out at Dryden, and he actually controlled the plane into the crash landing. Now, to make sure that
for those who don't know this, Fitzhugh Fulton was also the pilot for the 747 carrier aircraft that basically carried the shuttle orbiter on top of it if it landed at Edwards Air Force Base in California back to the Cape.
That's exactly right. And I watched it fly over Langley Research Center in Hampton a number of times. I guess just to show us that it was it was a good show. But anyway, we at Langley were very concerned because we knew a lot could go wrong, and the setup for the controlling of the aircraft was not the world's best. And unfortunately, at the time, there's ground effects had to be taken into account, and the pilot could lose control if he got real low. We practiced the landings quite a bit, or I should say they practiced them. I was not part of that. But they could only go so close to the ground. But so anyway, to make sure the fuel tanks were burst open, they had these what were called tank traps. They're these gigantic steel cutters, essentially, that would cut the wings open. Well, the aircraft came in, and Hugh Fitzhugh did his best. However, it sort of crabbed in a little bit, and it didn't hit exactly like they wanted it to. And instead of just cutting open the tank, it actually cut open one of the jet engines. And that ignition source was extremely hot, and the whole experiment went up in smoke and flames. What can I say? But we had a lot of good data. We had actually, the people at NASA we had fireproofed all our equipment, and we had our cameras, and we got a lot of good films out of that from inside the plane, actually.
You know, I remember watching that, and I knew this was a great experiment for this anti-misting fuel. And we watched the wing dip down and hit that pylon that cut it open, and it burst into flames. And I guess, did anti-misting fuels, did they take off after that, or did people not believe that it could do what they were supposed to do?
I think that was the death knell. I'll tell you else, it was very hard to get this anti-misting fuel to burn properly, and they had to run it through degraders to degrade it before it got to the engine. So it really died after that test, I'm afraid.
Yeah, that was a terrible failure, I guess, for the folks that were promoting anti-misting fuels. But I remember that, and so that's amazing. So you were part of the team that was basically taking the data. You have all these very expensive instrumented test dummies, crash test dummies, just like you do in an automobile crash, and that was so cool. And so now let's segue into the Columbia accident, right? We're getting close now for the 20th anniversary of Columbia. I know exactly where I was when that happened. I was training in Russia for a space station, a backup crew. But what were your thoughts when you heard Columbia crash, and then as information started coming in and you started processing it, you realized that a piece of foam hit the vehicle? Walk us through that. What were your thoughts?
Okay, Charlie. February 1st was my daughter's birthday. It was also a Saturday. So one of my colleagues up the street, Bob Doherty, who was in the landing group, they did a lot of tire work on the shuttle with a large carriage. Well, Bob Doherty would listen in and go, on the various messages and so forth with the people in charge, and he put out some emails about what was going on that I started reading, and I said, oh my God. So then, of course, I started looking at the TV and so forth. And also, I don't know why Bob Doherty got in such big trouble. Maybe I shouldn't say this, with the CAIB, but anyway, he did. But that's where it started. So after that,
wait, just to walk the audience back, I believe during the Columbia accident, I believe people at JSC did not contact anyone when the foam hit the vehicle. They didn't ask for help for anyone, but one lone email went out, and now I remember the name. It was Bob Doherty, because people at JSC, when they saw that foam hit, they thought maybe that might affect the landing gear, and Bob was the expert there.
That's exactly right, Charlie. And somehow or another, I don't know why, like I said, Bob got a lot of negative press on that, and I didn't think it was warranted because he just put the word out. Anyway.
Wait. Let me ask you another thing, Ed. This accident happened, I know the folks at Glenn, we're going to interview the folks at Glenn also, but didn't the people in the program office, when they saw the foam hit the wing, didn't they know that we had experts at Langley, like your team at Langley, like Matt Mellis's team at Glenn? Didn't they know that you existed?
Well, I mean, I didn't know those people down there personally. I did know Bob Doherty, and like I say, I kept up with things with him somewhat. But we had done some work on the X-38 and written some reports and so forth. So we had done impact work that was space related, but I did not have a working relation with any of the people down at Houston, the control people.
But the X-38, that was John Murator and the folks at Johnson Space Center, right?
Yes, we did a little bit of work on that as far as some landing simulations and so forth. That was about the only kind of space work that I had done before the shuttle accident. But the shuttle accident, once I heard about it, I mean, I got very interested, because I mean, this is something I knew that we could help out, but we weren't encouraged to join in. But we started talking to Throckmorton on conference.
Wait. You weren't encouraged to join in. So upper management was basically not saying, hey, call up Johnson and.
No, well, unfortunately, I don't know. Upper management, I think, told lower management not to join in unless you are specifically asked. And I know that that we were told don't join in unless asked, but unfortunately, we don't always obey, our management. So we started paying attention a little bit, because we knew that our help was probably going to be needed, and we knew there was a lot of good people out there that could help out.
So who at Langley said, you know what, could you guys help these guys at JSC? Who was the guy that went to you? Was it Del Freeman?
Darn, Charlie, there's holes in my memory on exactly how we did get involved. Like I say, I started talking on these telecoms with Throckmorton. He was down at Marshall, so I sort of backed my way in, I think.
Yeah, and I actually called up Del Freeman. I'm going to interview Del Freeman. He's going to be on the podcast with us. But I actually called Del Freeman. I said, you know what, we need Ed Fasanella and the team at the landing loads to work with the guys at Marshall. And Del was also the same way. I mean, Del told me exactly they weren't going to jump in unless they were specifically asked by JSC. JSC didn't want me to ask anyone, but I went ahead and asked Del because I knew Del.
Right. Well, I'm glad you did. We appreciate your help, because we put together a great team, and we had a lot of camaraderie. It was the most exciting time of my career, and I think I wrote more papers and did more work during that than any other project I worked on.
The other thing you told me, which a lot of the researchers that I have talked to, because I'm going to be writing a book about a research culture, right? And one of the things that's very interesting that some of the other researchers have said is, when I asked them, why do you get into this? Because they love to solve problems. And I know when I was first talking to you about coming on the show, you said the same thing. You love to solve problems.
Well, that's my mantra. I mean, if a problem out there, I'm like a pit bull. I get on it and I try to find everything else I can about it and work on it. And this problem with the foam, I mean, I knew about, inertial effects and high velocity. Just take a hurricane. I mean, there's straws that have been poked right into a fence post, and you say, how can that happen? Well, that's because the straw doesn't have time to bend, so it goes right in. And so with inertial effects and high velocities, all kind of crazy stuff can happen, but you can understand it and you can predict it. And but you have to do a lot of testing, and you have to test your tests, and you have to know what's what, and you have to know what you know and what you don't know, and you have to quantify everything. It's like climate change. It has to be quantified, and it's very difficult. In that case, they use a type of finite element also, but you're trying to model the whole Earth. All we were trying to model is just a leading edge and a foam, and also other debris like ice and composite material.
And I talk about a research culture, a research environment. I mean, this is how we grew up. That's how we do business. You go out, you try things, you fail, you learn, and you progress. And so when we put together the team, we had people from Langley, we had people from Glenn, Matt Mellis and his team, Kelly Carney and the folks out at Glenn Research Center. Dave Throckmorton was, I think he was a deputy director out there at Marshall, at Michoud.
Yeah.
No, Stennis, excuse me, at Stennis. And we put together a team of people to present to the program office, the shuttle program office at Johnson Space Center, what we could actually do with a team of people that did research in this area, physics-based approach. It took this team of teams. Walk us through how you guys work together, all the different expertise that you had to bring to the table, and the environment that your team was able to work together and do these amazing things in a pretty short period of time.
Well, it was a great effort, and there was a lot to learn. The various debris we actually started out with foam, of course, then tried to figure out how to model that. And at Langley, we had drop towers, and we could get a fairly high velocity with bungee assisted drop towers to get to actually crush the foam very rapidly, dynamically, and look at the forces that are generated. We took that. We even looked at the foam at low temperatures and so forth, and warmer temperatures, low temperatures. We took blocks of foam and did that in our drop tower. That was part of the work. There was the team up at Glenn Research Center, Matt Mellis, Kelly Carney, Pereira, and their group. And they, of course, they've been working ballistics for years, and so they shot foam. And of course, they have all the information on that. But we worked together. We had telecons. And that was before Zoom. We had telecons. I guess there were phone cons, phone talks. And we would discuss what we were doing. And also John Gabbers was very instrumental in our group. There were sort of, at the very beginning, there were sort of a large number of people that were saying they could do this modeling and could help. Everybody wanted to help. Let's face it, it was a national tragedy and everybody wanted to help. But the people at Johnson did pick a certain number of team players to be the core, and Langley, Glenn, Houston, and Langley, Glenn, Houston, Boeing. And
Boeing helicopter where John Gabbers worked.
Yeah.
And I remember when they were setting up to do this full-scale test, and I saw that they weren't going to instrument this full-scale wing leading edge. They weren't going to do any analysis. They were going to put a minimal amount of strain gauges on it. And the fellow that helped me put the brakes on was a fellow that was a vice president at Lockheed at the time that was observing the cave. And I told, his name is John Neer. And I told him, we could do a lot better than this. And I think that's how we actually got the attention and got in front of the program office. And do you remember when you guys were presenting some initial results? I remember we even brought in Sandia Labs, who had like an orders of magnitude, much more refined model than yours, looking at hundreds of parallel processes that they used to do the predictions for the bunker busters. And when they compared their analysis with your analysis, they realized that, hey, you guys, it correlated very well.
Well, yes, Sandia did get involved, and they did have a lot more resources than we did. And sometimes, it just takes the right hammer to crack the nut. You don't always need a sledgehammer. So we just came up with a very good model because we had a lot of test data to put into it. And we had ballistics people, we had impact people, and we had the various centers, NASA centers, and we all got together. We talked to the Sandia people. We saw what they were doing. We saw what the various people were doing, and we were just very happy, and a very, very good group, and a very hard-working group. And I think sometimes it's the tortoise and the hare. Maybe the tortoise wins.
And you talk about the different expertise. You had to rely on material scientists like the folks at Glenn that were developing these failure theories for the foam, failure theories for when the lamina and the fibers would fail in the RCC composite material. And as you're running these very small tests, that's the process that I like to call failing smart, fast, small, cheap, early and often. You're rapidly assimilating this data, you're validating your models, you're looking what's happening.
Exactly, Charlie. We had little samples of RCC, and we did impact tests on those, and we would take the little bending models, for example, doing a simple three-point bend with little small samples like 1 inch by 6 inches long. And we would study the inertial effects and the velocity effects, and there in our lab. So we had the lab set up, and we had a very good experimentalist, Satiris Kellis, who at the time was a contract employee, but he later joined as a civil servant. And he's done an awful lot of very good work for Mars sample return and so forth. I actually did some work for the Mars sample return too. But anyway, we had a really good laboratory set up, and we did a lot of testing. So we learned a lot about the materials. We even studied some of the ablative materials that are on the solid rocket booster, and we did impact testing on those. So in addition to the really high velocity that was done at Glenn, we did sort of intermediate velocity work, and we could extrapolate and pick up strain rate effects and so forth on the lower end.
That's right. And the other folks that you had on that team was Southern Research Institute, John Koenig.
Yes, that's correct. John Koenig he would actually do the testing of the materials and gave us a lot of good information there. We used his information to start. It was static testing, but it was a failure, but it was good information. That gave us an idea of what the strains, when it was going to break, and we had strain-based models for failure. And John Koenig was very important person.
And so that's the other thing. You not only did the foam, you also did ablatives, and you also did ice.
Yes, we did ice. That was very interesting. Matt Mellis was able to find a company in Canada that would make cylinders of ice.
Special ice flown in from Canada.
Beautiful stuff. And he shot it up there at Glenn, and we got boxes of it, and we stuck it in our excuse me, our bungee assisted drop tower, and we got a lot of good information on that stuff. Lower velocities.
And the other thing that your team did that you brought in, you talk about, you do work in experiments and also analysis, and the experimentalists are very important, was the work that Glenn Research Center was doing in full field observation of the impact test and actually measuring using photogrammetry, the deformations, and then you could calculate the strains and over the entire object, so that now you can compare it with your analysis, which was phenomenal.
Exactly. That data was beautiful. Those color charts of the strain, the deformations that they measured up there at Glenn, they had square panels that they would shoot, and they would send us the information. Then we would start making the models, and we had models that would predict that right on all the way up to failure, the deflection, the strains, the failure. So we used all that kind of stuff to perfect our big models. So you had to have little models, component models, and large models. So we had to have the whole thing. You got to start small.
It was a building block approach. But tell me something, when did you first learn that the folks that made the call up to space and said, you don't know, not to space, but to the program office, and said, you don't have to worry about it, it's not going to be a problem. They used this crater analysis. And when you looked at that equation that they used in the crater model and what it was based on, which was about 50 data points of foam that was about 3 inches cubed, and the actual piece of foam that hit the vehicle was 1,290 cubic inches. What were your thoughts when?
Well, I mean, that's just a small semi-empirical, almost like a spreadsheet model that they came up with, and I guess that unfortunately it was inadequate. So what can I say? It was just a simple model that really, I looked at it, but that's about it.
I know he's just such a nice guy. I mean, I don't believe if I was a sophomore in college, I would have believed that that someone would use that and extrapolate 400 times to predict a life and death situation, and then be so confident that they knew what they were doing. But they did, and we lost the crew, and we learned so much more because of people like you. And I just think the story and how your team operated is an exercise on what I would consider what every high-performing team, how they should operate. I mean, you had this geographically dispersed team, you communicated, you set up a website, you had technical interchange meetings, you had teleconferences, and you were transparently transferring this information and analyzing this information and sharing it and collaborating as a really great team.
Yeah, we had a great team, and we visited each other. We went to each person's location. We were on the phone all the time. Like I say, it was before Zoom and before a lot of the collaboration type programs that came along. Also, I want to mention some of the people at Langley that were on the team, because it was a team effort. There was Karen Lyle, who did a lot of the modeling, a modeling expert, Karen Jackson, Lisa Jones, Richard Boydnott, Satiris Kellis, and we had a fantastic guide with nuts and bolts, a very good technician, Nelson Seabolt, who's still working at Langley at 70 years old.
Wow.
He was a fantastic worker. But yes, it was a good collaboration. We worked off of each other. We wrote papers. We started. We didn't extrapolate. You just can't do that. You can't extrapolate you might extrapolate a hair, but you can't extrapolate orders of magnitude.
No. And, I was working for Ralph Roland in the NASA Engineering and Safety Center, which helped sponsor a lot of this effort. And back in the day, the team that missed the call and said the STS-107 was safe to come back and re-enter the Earth's atmosphere, the Leading Edge Structural Subsystem Problem Resolution Team, LESSPRT, was the name of that team. And after your team did such great work, I wrote up a little paper and I sent it to Ralph, and I said, you know what, we need to emphasize what I call the super problem resolution team, how it's supposed to work. And yours was a model that I think resonated with Ralph and the rest of the people high up in the NESC, that they could use this as an example of what could be done if we link real researchers with a lot of really good engineers and technicians. It could be geographically dispersed, and how the magic can happen. And, tell us about the leadership, because, this was a pretty much flat network that you guys worked in with no real directive kind of leader, so to speak. I think you had Glenn Miller, that was kind of your program manager, but you really tell us about it. Tell us how it all worked out, because you each had different areas of expertise.
Yes. Well, let me say also that the NESC was a great idea, Charlie. And I did a lot of work after the shuttle for the NESC, and the landing of how to land the next generation missions. But anyway, back to the leadership management. Glenn Miller, I think he was in the program office there at Houston. He sort of got it started. He came to visit us at our facility, and we had all the people that wanted to get interested into doing this work there. It was Sandy and Marshall and Glenn, and I think Glenn was there. We had a lot of people there. But I also need to mention that he turned it over to a couple of guys that were contractors at Houston. They were Boeing people, Darwin Moon and Mike Dunham. Darwin Moon and Mike Dunham did do a good job. It was later into the program that they came along, but Mike Dunham was a very good technical man, and Darwin Moon was a pretty good manager. So we did have help from them as far as what to do and how to. They put out goals for us to do and reports to write and that kind of thing. Then we got the chartist and all that kind of stuff in the
You know something. Darwin Moon was actually I know Darwin, and I was working with him a little bit. I believe he was the Boeing employee that was actually running the creative program back in the day.
Really, he didn't admit that to me.
Yeah. I think he was one of the guys that made some of the first calculations. You know, that program was developed by Boeing out on the West Coast.
Yeah.
And so I guess they certified people that were working at Johnson that could use that code. But it really was not designed to be used the way it was used. And Darwin knew that. Darwin knew that. I just don't think upper management realized that.
Exactly. And like the NASC is, like I say, a great idea where you get management that can talk to experts. But you know, you can't believe all experts either. You got to listen to everybody. And I think that's a consequence of the Columbia accident. NASA management wised up and decided, hey, we need to listen to everybody in the room. So that was one of the mantras: listen to everybody, let everybody give their opinion. Because the guy in the back that's a junior engineer, it could be that he happens to know something the expert doesn't know.
And you know, that's one of the attributes of a research culture. Back at Langley, when you read the SPs by the historians, it was that deference for the person with the knowledge. No matter what the hierarchical status of that person was, it could be the most junior person. If they had the knowledge, people listened to them. The other thing was a psychologically safe environment where you could argue, you could discuss. And I know that you experienced this with your team because there was an alternate team from Langley that were analyzing the impact differently. And you guys used to get into some nice, tense discussions.
Well, the other team was actually there at Houston that were modeling. They had a group that was modeling it. Yeah, we got into some discussions. It sort of got nasty at a few times. I hated that because but you know, sometimes you do.
You know, I can't remember who that would be at Houston because, you know, I was director of engineering there for a little bit, and we had folks that had done hypervelocity impact, but we had no one in Houston that actually did ballistic impact.
Well, you'll have to ask Darwin Moon or the name. I forgot the name of the fellow. He was a contract employee. He wasn't a civil servant, but he had his own code and his own method of doing things. And we were concerned about he was getting whether he was, well, what he was doing, I guess. But I don't even want to get into that.
Whatever he was doing, let's just make sure the audience realize when they actually ran that full-scale impact test with that very large, almost 2-pound piece of foam traveling at 545 miles an hour, and it struck that full-scale wing leading edge, you guys predicted beforehand it would see a large pizza box size hole about 14 inches square, and lo and behold, that's what happened.
Yeah, we did that, Charlie, but that actually wasn't near as good as our test that actually just predicted a crack or a small hole. That was catastrophic damage. And I think, you know.
And you were able to predict that?
Yeah, we were able to predict the little cracks and the leading edge damage that was small that could lead to big problems. So
that's right. That's right. And for the audience to realize, the leading edge is made out of carbon, which is totally combustible. You know, it oxidizes readily, but it has a very thin silicon carbide coating, right? Like 40 mils thick, very thin, very brittle. All you have to do is chip about a thumbnail-sized piece of coating, and you will burn the hole will grow, and the vehicle will be destroyed on entry. And what Ed is talking about is you had to determine what that minimal size damage was.
Yes, the acceptable damage. And we had the model of the silicon carbide layers and the RCC layers underneath. So we had a multi-layer program, and we looked at the strains and the so forth in each layer, so we could sort of predict whether it was going to chip off the silicon carbide and what was going to happen. But yeah, it was we then we started looking at ice and other materials. So we we spent years working on various types of debris and things that could happen in the model.
I don't know if you remember this, Ed, but not only did we, the power ramp came off when we launched and it went under our wing leading edge. We almost got hit with a much larger size piece of foam on our launch, but we also hit a buzzard on launch. Do you remember that?
Yeah, the buzzard. I'll never forget that.
We hit a buzzard right at the tippy top of the external tank.
We had to actually go up and model that.
Yeah, right.
Yeah, we modeled the buzzard impact too.
It would have been catastrophic if it would have tumbled on the other side of the tank and hit the orbiter.
Oh my gosh. You were lucky, weren't you, Charlie?
I'm still very lucky.
Amen.
Oh boy, Ed, you had such an amazing career, and I always remember you being this positive, happy-go-lucky, intense. There was never anything you wouldn't do. You always loved to do the work you did. And tell us a little bit as we close today, because we're both retired, Ed, what it was like in the early years working as a researcher, and then did you notice any changes before you retired in NASA?
Well, when working at NASA, you just take a popular place to work. You just take a poll, you'll find that all the government facilities NASA usually comes out number one, and the engineers that work there, they've always loved working there, and are dedicated and very hardworking people. I guess back in the old days, things have changed over the years. There's no doubt about it. But I think you've got the same thread of the type of people that go engineering. They're analytical type people, math oriented, science oriented. The engineers are, and they're still. They're still putting them out today that are very good. Look at the people working for SpaceX now. I mean, I don't know where they got all those people, but they must have picked up some really good ones, because when we studied, I did a lot of work studying a land impact landing, for the Orion program, and so did other people using rockets and so forth. But then I couldn't believe, we said, oh, well, it looks like we better stick with the water, but it looks like Musk came along and landed on a barge. I said, oh my God. So I think things changed a lot as far as the technology to allow that. But that was a great feat there. But yeah, things changed, but they're still the same. I think the same type of people, and it requires the same dedication, the hard work. And when people's lives are at stake, you really want to do the best, whether it's an automobile crash for safety, or whether it's a shuttle, or whether it's Orion, or whatever it is, or building bridges. No matter what you're doing in engineering, people's lives are at risk, and you want to do the best job you can because you know it.
Well, Ed, I talked to some of the folks that, when I flew in space, I don't know if you could see it, but my crew notebook, I had the Friends of Charlie network, the names and their telephone numbers and emails. And if we would have had an impact, Ed, I would have called you up, just like I called up Tom Horvath for the gap filler problem. If we would have had an impact and there was no damage detectable, I would have called you up just to make sure.
Well, there was a lot of good work done at various centers, including at Langley, on damage repair on orbit and so forth. It's a shame that the Columbia accident ever happened. And I don't want to talk about mistakes that were made probably, but anyway, I think NASA learned a lot, and we have to just go forward from there.
Well, buddy, I'm so happy you took the time to tell your story. There's so much more to it. If people want to get access to anything, do you have a website that they could go to, or they could ask me, and I will get whatever
have them ask you, Charlie, and you can contact me. I don't have a technical website or anything like that. I mainly since I retired, I worked for the NIA a while, but I worked until my 70s, and then I retired, and I mainly piddle with things now, and I do some editing on timepieces and horology and that kind of thing. So, but yeah, if anybody has any questions, I'd be glad to answer. You just send it on to me, and I'll be glad to contact them.
Will
And
do.
it's
And
fun.
thank you.
Yeah,
Thank you so much.
for asking me. And I never turned you down, Charlie. So
I know. And I just want to thank you for taking the time, and thank you very much. Enjoy retirement. It was great talking with you. Take
Same
care.
here, Charlie. Take care. Bye-bye.
We hope you enjoyed this conversation. If you learned something new and this story made you think, then share ITSP Magazine with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our columns. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.